Okay, so first I'd like to thank Avi for this wonderful workshop. I'll be talking about problems of the following type. Suppose you have a matrix property P, let's say the matrix has rank at most k or at least k, or the matrix is nilpotent or has some condition on the eigenvalues. The question that we are concerned with is, can we say something about linear spaces that such that all matrices in these spaces share this property? This is, of course, quite general problem, and we'll be more concerned with the simpler problem of what's the maximal dimension of a space of matrices all having a property P. These kind of questions appear in various mathematical areas, from combinatorics to, of course, theoretical computer science and even topology and algebra. And I'll try to give some kind of survey of a bias survey, of course, of several things that are related to this, and we'll concentrate on three examples. The first example has to do with spaces of maximal with maximal rank at most k. This has a combinatorial flavor, and I'll try to indicate the connection between this question and the matching theory in combinatorics. The second second topic is actually the complementary topic, asking for spaces whose minimal rank is at least something. This has more topological and algebraic topological character, and I'll try to give some hints about what goes into these results. And finally, we'll talk about linear spaces in nilpotent varieties, and we'll talk about the matrix case and perhaps about some Lie algebra generalization. We have some notation, standard notation. M of M cross N is just the space of M by N matrices over F. When N is equal to N, we'll just write M and F. Symmetric matrices are just denoted by sim n. Alternating matrices are skew-symmetric matrices with zeros on the diagonal. So this is just to take care of the characteristic 2 case. We'll write U tensor V for the rank 1 matrix, which is the column vector U times the row vector V. And we'll denote by, I'll call it R max, the maximal rank in a set of matrices, S. And R min will be the minimal rank, except that if S contains 0, then we don't take 0 into account. Okay, so let's talk about the first and simplest and perhaps most basic question, which is the following. What is the maximal dimension of a space of matrices, all of whose rank is at most k? Here are two examples. We take all matrices that had 0 in the last n minus k rows. This is certainly an example of a k times n dimensional space. Here we can have anything that we want. And here we have 0. Then the rank is at most k, of course. If we take the transpose of this space, we get this space, which also, of course, have the same properties. And the theorem, which is called, and as many of these questions are called generically Flanders type theorem for this result, Flanders theorem tells us that this is indeed the maximal dimension that can be attained. So k times n is the maximal dimension, and furthermore, this is attained only for these two examples, where what I mean by this is that, of course, these two examples under the action of GLN from both sides. So if you multiply this space by GLN, then some matrix from GLN, then again you get a space with the same properties. So this is a Flanders theorem, and the original proof was kind of algebraic and assumed that the field is somewhat large, and but it turns out that this is a completely combinatorial statement, and we'll try to I'll try to explain what goes into this. This is very simple, but actually we'll talk about something which is perhaps more interesting. What happens? Right. Namely about spaces of alternating matrices with bounded rank. Okay, so we ask the same question, namely, what is the maximal dimension of a linear space of alternating matrices of rank at most k? Now, the first observation is that since alternating matrices have even rank, then we may assume that this k is just 2t. And here are two examples, and in this case they are quite different. The first example is you take the upper left corner of size 2t plus 1 by 2t plus 1 to be any alternating matrix, and the rest will be 0. This clearly has rank at most 2t plus 1, but since it's alternating, then the rank is at most 2t, and so we are okay. And the dimension is 2t plus 1 choose 2. Okay. The other example, note that this does not depend on the size of the matrix, namely n. The other example is again quite simple. You take just the first two t rows to be anything except that here you need an alternating matrix, and here you transpose. So the rank of this matrix is at least at most t for the t rows and t for the t columns, namely 2t. Now what about the dimension? The dimension is t times n, except that we have to subtract, we have to take into account the fact that here we have an alternating matrix, so we have to subtract t plus 1 choose 2. Okay. And the theorem tells us that this is in fact the maximum between these two dimensions is in fact the maximal dimension that an alternating space of matrices of rank at most 2t can attain. So as an example of using this combinatorial approach, I'd like to give a sketch of this proof. And those of you who, well, all of you who know a little bit graph theory immediately see that this has a close connection to graphs. Why? Let us recall the following notion. Suppose that we have a graph, G equals to VE, and matching in a graph is just a set of disjoint edges. And the matching number is the maximal number of disjoint edges that you can find in a graph. Okay? It's a classical combinatorial parameter that's attracted a lot of attention. And a natural question is, suppose that you have a graph on n vertices, what is the maximal number of edges such that the graph contains at most a matching of size k, or size t actually. Okay, so here are two examples. One example is just taking the clique of size 2t plus 1. Then, obviously, you cannot put in here more than t disjoint edges. This has 2t plus 1 choose 2 edges, all in all. Another example is, well, take a clique on t vertices, this kt, and join each vertex to the rest of the vertices, n minus t vertices. Then, again, obviously, you cannot have a matching of size more than t, because any matching must intersect this red set, and the red set has only t vertices. So again, nu of this graph is t, and the number of vertices and number of edges is t times n minus t plus 1 choose 2. Well, just yeah, it's very simple to count. Okay, so we see that these numbers actually coincide with the numbers that we claim to be the best for the space of matrices. Now let's see why this is true. This is not hard to see. For this we need two concepts, or two ideas. Okay, so this is the proof idea. The proof idea is the following. We take a space of matrices, we associate with it a graph whose number of edges is exactly the dimension of the space. And now the main point is that it turns out that this graph satisfies that the matching number of this graph is at most the maximal rank over 2. Now, since the maximal rank over 2 is t, we can use the Erdős-Galai to bound the number of edges, but the number of edges is the dimension of S, and we are done. Okay, so we have to carry out this thing, this program, so to speak, this mini program, I would say, and let's see how we do it. Well, the first thing is how to move from a metric space to a graph. And this is very simple. You take the colexicographic order. I'll give an example in a minute on the set of ij's where I is less than j. And then you look at the matrix, and for the matrix you look at the first place where it's non-zero. It's a place ij, and then you put in the graph the edge ij. Okay, so this is a way of associating an edge with a matrix. And now suppose we have an alternating space. We look at all the non-zero matrices in the space. For each of them we associate an edge. Altogether we get a graph. So here is an example. The colexicographic order is this one. You start from 1, 2 to 1, 3 and so on. The leading entry of a matrix, say look at this matrix. So the leading metric, the maximal ij such that aij is non-zero is this, 2, 4. And if we have this space, alternating matrices, we can see that if y is 0, then we get the edge 1, 2. If y is non-zero, then we get the edge 2, 3. Altogether, we get this graph. So we found a way to associate a graph with a space. And it's clear that the dimension of this space is equal exactly to the edge, to the number of edges of this graph. Yeah. Okay. Now we need two notions to really carry out this mini program. The first one is the notion of Paphian. Paphian is a function which is about similar to the determinant of alternating matrix, and it's defined this way. You look at all perfect matchings of Kn. So take a perfect matching, K1 less than L1 and Kt less than Lt. You partition n into n half pairs. You look at the sign of this permutation, namely 1, 2, K1, L1, and so on. And the Paphian is the sum of the C in place Ki, Li over all n half pairs times this sign. And it's a classical and very useful result that says that the determinant is just the Paphian squared. Okay? So in order to check for non-singularity, it's enough to check the Paphian. So this is one ingredient. The second ingredient is what's called the Combinatorial Nullstellensatz. And this is the following result. Again, it's quite simple, but turns out to be useful. Suppose that we have a polynomial in variables x1 to xt, and we look at the total degree. So the total degree is the maximum of the sum of the alpha i's, such that the C of alpha 1 to alpha t is non-zero. And the Nullstellensatz of due to Noga alone tells us the following. Suppose that the degree of G is the sum of di's, for some di's, and the coefficient is non-zero. And now suppose that we have sets in our field. The field can be anything, actually. Lambda 1 to lambda t, each of size bigger than di, strictly bigger than di. Then we can, and there is a choice of elements, small lambda 1 to small lambda t from these sets, such that g does not vanish on this substitution. Okay? So you can see that this is, yeah.
This is a tight version of the Schwarz-Zippel lemma that was used all over the place.
Yeah.
If the sets were a little bigger than a random choice would do, here it's just precisely this one choice would do to make the polynomial non-zero.
It's very closely related to these ideas of Schwarz-Zippel. Okay, so now we have these two ingredients and we are more or less done. Why? Because actually what we have to prove is that the gist of the idea is if we have B1 to Bm alternating matrices of size n where n is 2m, and if these places, leading places in each of the Bi's together form a perfect matching, then there is a matrix in this space, a linear combination of the Bi's, whose rank is the full rank. Okay? So how do we go about proving it? Well, we look at the polynomial, which is the Pfaffian of the combination with xi coefficients of B1 to Bm, so the sum of xi Bi. Now, this is a polynomial of degree, of degree exactly, n. Now, right. Now, the claim is that x1 to xm appears in this polynomial with a non-zero coefficient. This is something that you have to prove. There is some minor combinatorial trick for doing it. But once you do it, then you deduce that by the combinatorial Nullstellensatz, there is some substitution in the base field such that the determinant of the sum of the lambda i's, which is just the f lambda 1 to lambda m squared, is non-zero. And thus we are done. Okay? So modulo this observation that actually x1 to xm has non-zero coefficient, and you can guess what the non-zero coefficient is. It's simply you take the places of the matching. There are m places of the matching, and exactly when you take the product. When you take the product here of these CIs, they are guaranteed to be non-zero. And it turns out that you don't see any other coefficients for x1 to xm. So we know that it has at some point a non-zero coefficient, but it turns out by some combinatorics that it has in no other place will a non-zero coefficient appear for x1 to xm, and so we are done.
So by the way, it's a kind of riser formula.
It's a kind of riser formula. Okay.
So the formula, it's kind of riser formula to compute instead to compute number that sum of. So say you want to express that coefficient.
Yeah.
Okay. So riser formula really does polarization. So you get polynomial. Right. You want to extract the coefficient x1, xm. Okay. It goes over Boolean cube and with certain weights, and it gives you one of those. If that coefficient is not zero, one of those expressions will be not zero.
It's much more general. You don't have the usual symmetry here. I mean, it's an arbitrary matrix space.
Yes, but the riser formula does not need symmetry, really. But it's a formula. It's a formula to extract coefficients from.
But it's the permanent of the complete.
No, it's much more general than that.
I have a different question. So it seems that in this course, of course, to prove this lemma you were hiding from us, you do need the colexicographic ordering and the choice of the way you choose the edges from the base matrices. it seems that something stronger is being proved, not just that the rank, not just the lower bound on the rank, but actually that there is a triangular matrix in the in this space. And this, it seems that in many of these combinatorial arguments this holds, and but sometimes the rank doesn't show itself in this way.
Yeah, you are completely right, and in many cases, this type of associating, this type of argument of associating a graph to a metric space and then arguing somehow appears in other instances for, say, for example, in handling spaces of nilpotent matrices, and indeed you get something stronger, but
it
I
just
don't.
seems that of course, in the polynomial identity testing cases, I think that are hard. Maybe it's not.
No,
it's not so.
Yeah. Okay. Okay. So there are some other versions. For example, one can talk about spaces of symmetric matrices with bounded degree, and here again you have a similar argument, but it's a little bit more complicated because you don't have a graph. You have a graph with loops, and but again you can do something, and there is again a result that on one hand you have when t is very big relative to n, you have that this wins, and when n is big, then this wins, and you take the maximum between the two. Okay. Now you can ask. Going back to the alternating case, you can ask what happens with higher exterior powers. So let us recall that if we have a vector space, then wedge P of V is the P's exterior power. It's defined as follows. You just take the Pth tensor power and divide by these identities. So V1 wedge Vp is equal to V pi 1 to wedge V pi P times the sine of pi. And
To the characteristic, not to.
Yes, actually we'll work with C or okay. Now I have to tell you what kind of rank are we working in, but let's first take what's called the minimum rank, namely rank 1. Let's talk about decomposable tensor. Decomposable wedge product are just V1 wedge V2 to wedge Vp. And now we have the Plucker embedding, which embeds the Grassmannian of the p-dimensional linear spaces inside the projective space determined by this vector space. This is a vector space of dimension n choose p. It's very big. You put inside this the Grassmannian, so you have some kind of variety which lies inside this, and the mapping is take the linear space spanned by V1 to U1 to UP and associate with it the point U1 wedge U2 to wedge UP. Okay, and now we can ask what is the maximal space, linear space, that lies in the Grassmannian under this embedding. So of course the Grassmannian is an abstract variety of dimension p times n minus p, but now we embed it into the projective space, and we can ask what is the largest linear space that lies inside this. This is a classical problem, classical result, and it says the following. There are two types of maximal linear spaces. The first type is the following. Take a p plus 1 dimensional space in V and take all the p spaces inside it. Okay, so this is one example of a collection of points inside the Grassmannian, and it turns out to be flat. So even though in this representation you don't see that it's flat, it's actually flat, and we'll see that in a minute. Another possibility is, well, here we took a p plus 1 space and took all the spaces, p spaces contained in it. Another possibility is take p minus 1 space, u prime, and take all the p spaces that contain it. Okay? Yeah.
Just to connect it to what you said in the very first slide, when you talk just about the Flanders theorem and the rank K matrices, what's the maximum? It's sort of the same question, but you are talking about the Grassmannian itself, just K subspaces of n-dimensional space, and you are asking for a linear space inside it of maximal dimension. Is it
in a minute we'll just go to the direct analog, to the exact analog. And here we actually go to the exact analog. So now I go back to spaces of tensor in a linear space. This is our linear space, wedge P of phi. So when P is equal to 2, it's just the alternating matrices. Here it's just the P vectors. We'll call it P vectors. And the claim is, or this claim is, that if W is a linear space of decomposable P vectors, so it's a linear space and all the elements there can be represented as U1, wedge U2, wedge UP, then there are two options for a maximal for a maximal such space. One option is take wedge P of U, where U is a P plus 1 dimensional space. And now, okay, and another why is this of rank? Why is this decomposable? Because you see, if you have take two elements, U1 wedge UP, and suppose that we have another one, V1 wedge VP, and all of them lie in some P plus 1 dimensional space. Now I claim that the rank of this can also be represented as this is equal to some W1 WP. Why is this? Because if you take these two spaces, these are they are p-dimensional spaces in a p plus 1 space, so they intersect in a p minus 1 dimensional space, and this p minus 1 dimensional space, suppose take a basis of this p minus 1 dimensional space, and you can add for each of them this p. Okay, so this is an analog of the fact that skew symmetric metrics can have only even degree. Okay, so this is one example. Another example is even simpler. Just fix V1 to Vp minus 1 and take all vectors, all p vectors of the form V1 to Vp minus 1 wedge V. Then clearly this has all of them share this p minus 1 first vectors, and certainly the rank of any combination will be, or any combination will be decomposable. Any questions?
The notion of maximal, you need not extendable or
right.
dimension?
No, not extendable.
Not extendable.
This is a maximal in the strong sense. Yeah. Usually you will not be able to say anything of that strong, but this is actually true. Okay, so what about the dimension? So the dimension is certainly a consequence of this argument that dimension is most p plus 1, the maximum between p plus 1 and n minus p plus 1. Okay. Now I'd like to talk about higher rank. So for this we need the notion of a rank of a p vector, and quick disclaimer is that this is not what you serious guys regard as rank. This is just a simple linear algebra computable quantity that we'll call the rank just for this talk, and it defined as follows. You take a p vector, a p vector, an element of this, and you write it as some sum of these things. And now you want you define the enveloping space to be the minimal space such that this W belongs to a wedge P of U. Yeah. Okay, and you take rank of W to be the dimension of this space. This coincides with the usual rank when we have alternating matrices. For example, suppose that we have this guy. So this is a combination of what? Four decomposable vectors. And on the face of it, it lies in wedge 3 of a 6-dimensional space, because we used E1 to E6. But in fact, if you write it as follows, as E1, E2, E3 plus E4, and again E3 plus E4, E5, E6, you find that it lies actually in a wedge 3 of 5-dimensional space only. Okay, and it turns out that you cannot do better. The rank here is 5.
Does it have another interpretation just as a tensor rank for anti-symmetric tensors?
No, it's not.
It's much smaller.
Yeah, it's a small thing. It can be at most n and the rank of tensor.
I think if we consider any tensors not anti-symmetric, this is a rather common notion. Say like W is in V1, tensor V2, tensor V3. Then we try to replace V1 by smaller subspaces such that V is contained in there, and then we get 3 numbers. Like three ranks, what you call it, but it's rather the dimensions.
Yeah, exactly.
It's very common to look at this.
Yeah, it's not it's of course not a new notion. It's a
say the tensor is concise. I mean, in my situation, if this you cannot put it into a smaller tensor product.
Yeah, you want to put it in the smallest word that you can. Yeah, this is a common notion, except that it's not our heart's desire, but at least this is something that we can handle. It's computable. It's just a linear algebra thing, and one can ask suppose that we have a space of matrices, a space of p vectors of rank at most k in this sense, rank in our sense. Then what is the maximal dimension of this space? Okay, so there is an answer. It again depends on matching theory. Now I have to. It's not written here, but we have to work over an infinite field of characteristic not equal to 2. And again, we have an expression which is similar to what we had before, and I think I won't go into the details except to say that it involves some extremal problem for hypergraphs, which is a kind of analogous to the Erdős-Galai theorem and some other things. Yeah, okay. So one can again find the maximal dimension here by combinatorial methods.
But in finite characteristic, one can get something bigger. In finite characteristic, one can get bigger.
Actually, I think that no, I don't think so. I'm quite sure that it depends also on kind of Nullstellensatz, which seems to work for this very special case over any field. Yeah. Okay, I won't go into this detail. Okay, now the PIT problem, which is in the back of our minds throughout this conference. The PIT problem is, of course, much more general than what we consider the numerical invariant that we considered here. We have A1 to AM. Can we compute the maximal rank in polynomial time? Now, as we know, it has a very simple probabilistic solution. You just take random x1 to xm, you substitute them, and since the maximal rank is generic, then we'll usually get the maximal rank. Now, one can ask, are there special cases, special spaces families of spaces where we can get a deterministic algorithm, then the situation is, as far as I know, is rather poor, and there are deterministic algorithms when all AIs are of rank 1, or there are skew symmetric of rank 2. And even this thing, the experts tell me that they are not sure that there is actually an algorithm, but okay, so let's talk about the rank 1 case, which is really simple, and as a consequence of a very elegant combinatorial result. Suppose that we have U1 to UT and V1 to VT in Fm and in Fn, and we look at the space generated by the rank 1 matrices UI tensor Vi. The matroid intersection theorem of Edmonds, this is a result from the early 60s, gives us a min-max characterization of the maximal rank. It says that, well, the maximal rank is exactly equal to the minimum of all partition into two parts of the index set of the vectors, and take the dimension of UIs in the first index set plus the dimension of the VJs in the second index set. Now, it's clear that this maximal rank is at most this, because if you split your linear combination of these tensor first as the sum of UI tensor Vi with some coefficients over I in I, and then the sum of Uj tensor Vj over J in not in I, then the first one is at most the the column rank, the column rank, which is exactly the rank of the dimension of the UIs. Second one, its rank is at most the row rank of the VJs, and so we get this inequality, this weak duality. But in fact, there is a strong duality, and the strong duality actually gives rise to an algorithm, and which also comes with this theorem. There is a polynomial time algorithm to determine the maximal rank. Now there is what about rank 2? In the rank 2, the situation is considerably more difficult, but there is still a result due to Lovász, which is the following. Suppose that we have a space generated by rank 2 alternating matrices, so U1 wedge V1 to UT wedge VT. Then the claim linear matroid parity theorem of Lovász tells us that the maximal rank is at most the minimum of this expression, where we take the minimum over all subspaces A and B1 to BK, where our space S is contained in A wedge V plus the sum of wedge 2 of BIs. So you take a space A and you tensor it, and you take the wedge product of it with everything possible. This is one summand, and then you have these BIs, say B1, B2, B3, and you take just the alternating matrices that are generated by this space. Then again, it's clear that the maximal dimension is at most this. Why? Because look, split an element according to this splitting. Then the part here has rank at most 2a, because it's a1 times something plus a2 times something else, and so on, and each something contributes 2, so it's 2 times a. Now what about this? Each of these contribute the maximal rank of a tensor here, but the maximal rank of a tensor here is the dimension over 2 lower. Well, it cannot be. I mean, if this is If this is even, if this is odd, then you lose one in the process. So it's 2 times d dame of bi over 2 lower value. Okay.
Is the V8 wedge in the capital V is F?
I'm sorry?
The S contain A and then wedge in the capital V.
Right, right. You just take a wedge of A with anything
Like
possible. Like
F to the N.
F to the n, yeah, exactly. Okay, so okay. Now the interesting thing that actually this is an equality, and this is a nice result, and it, as far as I understand, it comes also with an algorithm, but there are some well, Gabor tells me that he's not sure about it. I'm not sure that he's here. Yeah, but yeah. Okay. This until recently, I think, was the only examples where you can actually have an algorithm. But here is another very recent example, and in a way, it's a dual of the Lovász case. Now here you take again U1 V1 to UT VT, and you take the wedge product. But now you take a different slice of the 3 tensor, and now you take, instead of the linear combination of the UI wedge VIs, you take the matrices which are generated by the columns U1 V1 times X and so on. This is again a metric space, and it's a very recent result of Orit, Raz, and Avi, that there is a polynomial time to determine this the maximal rank also here. And one can wonder if there is some connection between the Lovász result and this result, but nobody knows. Well, at least Avi doesn't seem to think so. And one should remark that their motivation is they are looking for a polynomial algorithm to deciding rigidity. And in fact, this result gives an algorithm to decide rigidity in the plane. This was also done earlier by Lovász and Yemini, but this is a new idea, new direction. So one curious thing that I'd like to point out is the following. We don't fully understand this phenomenon, but suppose that we start with a space of matrices, but I'd like to write it as a subspace of home of U V, so all linear maps from U to V. Now we can view U as a subspace of home SV simply by cutting the tensor, splitting these 3 tensor differently. So now U operates.
Just to make sure, when you refer to a tensor, you have a space of matrices, so they have a basis. So it looks like a tensor. It's just several matrices.
Right.
You can look at them in different levels.
Yes, and more concretely, if S is contained in home UV, then U is contained in home SV also. Yeah.
May I ask about that previous slide question, please? So is this rank the same rank which shows up in that operator rank, this one?
No.
No?
Well, I don't think so, no. No, it's a different one. It's a different one that arises naturally in graph rigidity, but it's a different one, as far as I know.
So, okay, so you can also view U as a subspace of home of SV. Now, one can show that actually the maximal rank in U, if you view U as a space of operators, the maximal rank in U is bigger than the minimal rank is at least as big as the minimal rank in S, where the minimal rank is, of course, without the 0. And actually, there is a more refined result here. So it's a kind of a weak duality of some things that of the rho max and rho mean, but it's not a strong duality. But okay, this is just a remark. Okay, now if our motivation is the PIT, one can ask, we found a maximal rank. Can we say something about the maximum spaces, maximum in the inclusion-wise meaning? But this is not simple, because if you have a space generated by rank 1 matrices, then indeed there is a statement about the maximal spaces that occur here of singular spaces. So a maximal singular space generated by rank 1 matrices is just obtained by taking n, say n half rows, and everything is 0 here, and n half minus 1 columns, and everything zeros here, and adding them. Then what you get is a space, a singular space, of course, because n half minus 1 plus n half is less than n. And this is a maximal space, and anything that's singular is contained in such space. This is an immediate consequence of Edmond's theorem. There is an analogous statement for rank 2 alternating generation. So maximal spaces in the inclusion-wise sense of singular spaces generated by decomposable elements are of this type. You just take n half minus 1 spaces, three-dimensional spaces in general position, and you take their wedge and you add it up. Actually, here it should be just sum, not it's actually direct sum if they are in general position. And this is maximal, and this already has small dimension, just 1.5 n. And there is even a much more striking example of Drysma that says that for any n, for infinitely many n's, there exist 8-dimensional maximal singular spaces in M and C. So there is just a constant dimensional singular space that is maximal. You cannot, any matrix that you add, this perhaps tells us something about the difficulty of PIT, because indicates at least that it's not a simple problem. Okay. Okay. Now I'd like to move quickly to the other question, which is of different character, but I still think that it's interesting. Now we talk about spaces of rank which is bounded from below by K. So matrices that have spaces that have only high rank. For this, we need just some baby algebraic geometry. We look at R and K, which is the space of the variety of matrices rank at most K, and we want to ask what is the maximal dimension of a space, which is, so this is the variety, and we want a maximal space that or a space that avoids this variety. So if this is the variety of matrices of rank at most K minus 1, we want to ask what is the maximal dimension of a space that does not touch it. Okay. Okay. When F is algebraically closed, then R and K, the space of matrices of rank at most K, is an irreducible affine variety of this dimension, and therefore the dimension of a maximal of a space of rank at least K matrices must be at most the complement of the codimension of this variety, which turns out to be n minus K plus 1 squared. Okay, and in fact, if you take a random space, it will intersect it in a finite number of points, but you can actually avoid it by just moving it a little bit around. You can avoid it, and there exists, and this is a concrete example. There exist spaces of matrices of rank at least K of this dimension, and actually, you can put an n minus k plus 1 square dimensional subspace with this property inside here. Yeah, it's you can think about it. It's a simple idea. You just make sure that in each row, if the row is not completely 0, then its weight is at least k. This is just a coding theory over C, which is simple. Now, what happens with finite fields? Note that here we had n minus k plus 1 squared. Over finite fields, the situation is drastically better or worse. We can find spaces of dimension n times n minus k plus 1, which have rank at least k. And the construction, this is due to Ronnie Roth, and here is a very simple construction. You think of fq to the n, the space of the coordinate space of dimension n over fq, as the field of q to the n elements. Now note that for this field, the function, the polynomial x to the q to the j, is a linear function. Because x to the x plus y to the q to the j is x to the q to the j plus y to the q to the j. So this is a space of linear functions. When you take these polynomials of degree q to the n minus k with coefficients in fq to the n, this is a space of matrices or of operators. Its size is q to the n minus k plus 1, because in each place you have q to the n choices, and you have n minus k plus 1 places. So its size is this, so its dimension is just this exponent. Now, the claim is that the rank here is at least k. Why? This is very simple, because this polynomial has at most q to the n minus k roots, because this is a polynomial of degree q to the n minus k. Therefore, the dimension of the kernel is at most n minus k. The rank of G is at least k. Okay, so this, in contrast with the algebraically closed case, we get large spaces. Now, what happens if we go to the other spaces, the other fields like R? Now, here the situation is much more interesting, and I'd like to spend a few minutes to talk about this. Okay. Here is a definition of the Radon-Hurwitz Radon number. So you have n, and you decompose it as an odd number times the power of 2, and the power of 2 is 2 to the gamma plus r delta, and the Hurwitz Radon number is 2 to the gamma. It depends only on the even part, and it's 2 to the gamma plus 8 delta. So this is, if n was a 2 power, it's about 2 log 2 of n. Okay? And now one can ask, and this is the question that we are concerned with, what is the maximal dimension of a space of non-singular matrices? So on the face of it, it's quite hard to find such space, because, for example, over the complex numbers, you cannot have more than one-dimensional space of non-singular matrices, because if you have two matrices, say A and B, then you take A plus xb, you take the determinant, it's a polynomial of degree n, and it has a root. So this two-dimensional space will contain a singular matrix. But it turns out that over Rn, you can find small, for sure, but non-trivial spaces of non-singular matrices. So here is one example which we all know. For example, if you take xy minus 1x minus yx, where x and y are in R. So the dimension of this space is, of course, 2, and it's non-singular. Okay, so and the question was, what's the maximal dimension of a non-singular space? And there is an amazing result due to Hurwitz, Radon, and Adams, which tells us that F, R, and N is just HR, the Radon-Hurwitz number. When n is a power of 2, it's about 2 log n. Okay. Now, the lower bound is old. It's from the 20s or even earlier, and it's due to an explicit construction of Radon-Hurwitz. The upper bound is from the 60s. It follows from a result of Adams, which is much more general on the maximal number of vector fields on a sphere. So I'd like to say a few words about this. Now, first about the construction of Hurwitz and Radon.
What is x and y are 0?
I'm sorry?
Can you make x and y 0?
Yeah. I mean, singular means that we don't take 0. 0 is always, we don't take.
So the condition is x, y is in R and neither is 0, or both are not 0?
No, they are. No, this is.
Oh, it's in the 0 matrix.
Yes, of course.
It's either the 0 matrix or
Or
it's higher.
non-singular, yes.
Yeah, except for the 0 matrix, it's we always the minimal rank. We always have the 0 matrix. So the construction of Radon and Hurwitz in modern terms can be thought of depending on the Clifford algebra, which is interesting in its own right. So it's the Clifford, the CT Clifford algebra is generated by E1 to E2 modulo the relations EY squared equals to -1, and EY EJ is equal to minus EJ EI. One can think of it as a kind of generalization or a quantization of the wedge of the exterior algebra. And so it's an algebra with its dimension is 2 to the n. It's just 2 to the t, right? It has this basis, and it has this very curious periodicity property, which tells us exactly what are these Clifford algebra. So for the first 7 ones, the first one is R, the second one is C, third one is the quaternions, and then it's either sum of Clifford algebras or matrix algebras of Clifford algebras. Okay. So now, what's the connection between Clifford algebras and matrices of full rank? It's through representation theory of Clifford algebra, which actually is not difficult using the classification. So representation of CT on an n-dimensional vector space is just an homomorphism from CT to the endomorphisms of W. Now, I claim that if you have any such homomorphism, then this space, so a combination of these matrices, rho of EI, where I goes to 1 to t, from 1 to t, then this space is a t-dimensional non-singular space. Why is this? Let's just do the computation. Suppose that we have a matrix in this space, and suppose that this matrix times V times W is 0. Then multiplying this expression by sum of xi rho of ei, what we get is exactly this times W. But this, on one hand, is minus sum of xi squared because of these relations of the Clifford algebra. On the other hand, it's just operating twice on W by this element, which is, well, the first one was 0, certainly the second. After doing it again, it will be 0, 0 again, and therefore the xi's are all 0. So we have ready-made linear spaces of matrices which are non-singular, and now now using the classification of Clifford algebra, it's easy to show that you can act on Rn by Ct provided that T is at most HRn. And this means that Frnn, namely the maximal dimension of a space of nonsingular matrices, is at least HRn. So here is one example that corresponds to C1, which is C, just a complex number. The second example, which corresponds to C2, this is the quaternion. This, which is the quaternion, is this example. Just write the multiplication table of the quaternion. You get a four-dimensional space of 4x4 matrices, which are all non-singular. And actually, one can ask, when is the dimension, when you can get a dimension exactly n? This happens only for 1, 2, 4, and 8, and it follows from this, but was actually proved much earlier.
If you allow affine subspaces or shifts of subspaces, you can do much higher range, right?
Yeah. If you yes.
And this of the matrix can be constants also.
Right. You
can put one on the diagonal.
Yeah, and then
have whatever you
yeah.
want.
Yeah, actually, it's
a very different question.
Yeah. It's you can get actually the right number is n choose 2. You can get n choose 2. Okay. I'd like to say a few words about this. So we are getting further away from the topic of this conference, but let me nevertheless say a few words about the upper bound, because the upper bound is kind of interacts with topology and is quite interesting. Now. Let's go to vector fields on the n-1 sphere. This is very intimately connected with this notion. So a vector field is, as we already know, a vector field is just an assignment of a vector to each point in the tangent space in a coherent, continuous way. And one can ask, what is the maximal number of pointwise linearly independent vector fields on a manifold? So, for example, here you can say, I don't know, how many vector fields you can put on, specifically on Sn-1, so that they will be linearly independent for all x's in Sn-1. This was a classical problem that was finally solved by Adams, and the exact result says that you have exactly Rn-1 vector fields over Sn-1, which are independent. Now, note that when n is even, okay, when n is odd, for example, n is Sn-1 is S1. Okay, so when n is even, you do have at least one vector field. On the other hand, when Sn-1 is S2, you cannot even have one vector field because of Harry-Bohr theorem. Okay. Now, Adams' theorem tells us actually that if you translate Adams' theorem, it implies that Frnn is at most Hrn. Why is that? Because suppose that we have a non-singular space of matrices in M and R. We may assume that AT is 1. The last one is just the identity. And then by doing a Gram-Schmidt orthogonalization on the AIs, we obtain a vector field. So this will be vector field on Sn minus 1 because this is orthogonal to X. And so we'll get the T minus 1 vector fields on independent ones. It's easy to see that they are independent because this is a non-singular space. And then the result follows from Adams' theorem. But in fact, for the proof of Adams' theorem is a difficult theorem because it uses some heavy topology. But in fact, for the proof of this specific case, you don't need Adams' theorem in the full-blown case. You just need the additive structure of the K group of Rpn minus 1. So what is the K group of in this case? I'll just briefly tell you this story. The K group classifies vector bundles on a manifold, and it turns out that in Rp R minus 1 it's a 2 group. So it's this 2 group with this lambda, which is this thing. So actually we do understand this group completely. There is also a multiplicative structure, but we need only this additive structure. And it turns out that using this additive structure, you can prove this upper bound on the dimension of non-singular spaces quite easily. So here is the proof, but I'll just skip it. Yeah. Okay, so I have just few minutes, so I'll tell you something about nilpotent matrices. Now, suppose that we need, and this actually this is actually related to affine spaces of non-singular matrices. But let's look at this question. Suppose that we have a linear space of nilpotent matrices. Now, what can be the maximal dimension of this space? Well, an old theorem of Gerstenhaber tells us that the maximal dimension is simply attained by this type of space. So just strictly upper triangular matrices. And equality happens only when the space is similar to such space. One can ask what happens if you restrict to.
Just a second.
Yeah, so these are certainly non-singular. It's nilpotent. The dimension here is n minus 1 plus n minus 2 plus 1, which is n choose 2. And this is the best that you can do. One can, of course, ask what happens if we restrict ourselves to linear spaces of nilpotent antisymmetric matrices or nilpotent symmetric matrices. So as we learn in the first year, if you have a space of the maximal dimension of a space of nilpotent real matrices is 0, because any matrix which is symmetric, and real has eigenvalues, and if all these eigenvalues are 0, then this matrix is 0. So if we replace C by R, then we get 0. But on the other hand, if we look for symmetric nilpotent matrices, then there are very large spaces of such linear spaces of such matrices. This is an example. Well, I mean, it's hard to see here why this is. It's easy to see why it's symmetric, because we took X to be strictly upper triangular, and we took Y to be symmetric. It's a little hard to see why this is nilpotent, but believe me, I tried it, and it's nilpotent. And the dimension here is n squared over 4, which is what we want.
So what exponent, like what power do you have? Is it the square at 0, or is it the high power?
No. It's the power is m.
So you want to make y.
Yeah. I want to make y. So, yeah, but this is just an encoding of just much simpler space. One can ask what happens in this question makes sense in Lie algebra too, and this will be my final slide. Suppose that we have a semi-simple complex Lie algebra. It works for somewhat more general cases, but the claim is that just as in the matrix case, when we have say SLN, if we have a space of G, of the semi-simple complex Lie algebra, which consists of odd nilpotent elements, namely elements where the adjoint action is nilpotent, then the dimension of W is at most the dimension of the size of the set of positive roots, and you can imagine that such result is true simply because if you look at the nilpotent matrices, all nilpotent elements, there is the killing form is a symplectic form there. So in a symplectic form, in a space, in a linear space with a symplectic form, we know that the maximal linear space that lies inside it is at most of dimension half. So here we get even slightly better than half dim G, just the dimension of n plus, and there is a strengthening of this, this is easy. This is quite hard to show that actually equality only occurs when W is conjugate to n plus. Yeah, so I'm done. Yeah.